Okay, so good evening all. Today we'll start week 7 for the problem solving session. So in the week 7 lectures, further details about the AJ and screw dislocations are studied and their characteristics are mentioned in the lecture videos. So we will discuss the problems regarding that. So in this question, we have asked that consider the following body center cubic dislocation reaction. Prove first question is prove that this reaction will occur or not. What kind of dislocations are the A by 8 110 and A by 4 112? What kind of crystal imperfections results from this dislocation reaction? And what determines the distance of separation of the A by 8 bar 1 bar 10 and the A by 4 bar 1 bar 2 dislocations? Okay. So how we check whether a reaction between a dislocate Berger vector will happen or not? So we check by the energy consideration. And if energy is reducing because of dissociation. Good evening, Athar. Can you see my screen? Okay. Okay, so we'll discuss the problems regarding the week 7 lectures. So in the week 7 lectures, the professor studied about the means taught about the dislocation reaction jogs and kinks and the further characteristics of the edge and screw dislocations. So we will discuss the problems associated with that. So here the first question says that consider the following body center cubic dislocation reaction. Prove that this reaction will occur and what kind of dislocations are the A by 8 110 and A by 4 112 and what kind of crystal imperfection results from this dislocation reaction and what determine the distance of separation of these dislocations. So how first we check the occurrence of this Berger vector reaction by checking the energy. If it reduces with dissociation, then this reaction is feasible. So we'll calculate the energy for both sides. So for left hand side, the B1 square will be A square by 4. This will give 3A square by 4, or around 0.75 A square. For the right hand side, the uh, B2 square plus B3 square plus B4 square will be A square by 64, 1 square plus 1 square plus 0 plus A square by 16, 1 square plus 2 square plus A square by 64, 1 square plus 1 square plus 0. So this will, sorry, this will be, these terms are same. So this will be A square by 32, sorry, 1 plus 1 is 2, and 2 will be, sorry, 64, 2 square will be 4, A square by 64 plus A square by 60, this will be 4 and 6. So this will be 7A square by 16. So the if we calculate this, so the 3A square at the left hand side is greater than 7A square by 16. So as energy is reducing with the dissociation, so this reaction will occur. Next, we have asked that what kind of dislocations are these A by 8110 and A by 4112. So when a dislocation dissociates into a small dislocation with a small Berger vector, so that dissociated dislocations are called partial dislocation. Means if we check here, so this dislocation is full, and when it dissociates into small Berger vector, so dislocation, so that is called partials of a dislocations. So these three are the partials of this full dislocation. So that's why we call it partial dislocations. C option, we have that what kind of crystal imperfection results from this dislocation reaction. Yeah, so once the partial form from this full dislocation, so that create a region which is called stacking fault. Stacking fault means atomic arrangement got changed. So one if we have this B1 dislocation that dissociates into three parts or two parts. So these B2, B3, and B4. So the partial dislocation will generate an area in which the atomic arrangement will be different from the B1. So that is called this area is called as the stacking fault. And this because of this dissociation, some energy is associated with this partial and the region between these. So that energy is called as stacking fault energy. This is written as gamma as energy of the stacking fault. So this is given by the multiplication of Berger vector uh, divided by the distance between these partials. So as we can see that the energy gamma SF is inversely proportional to the distance between these partials. So if dislocation partial are wider spread, so the energy will be less. And if the distance or between partials is less, so the energy will be high. So we have asked in the third the question, what determines the distance of separation of the E by 8 bar 110 and the E by 4 bar 1 dislocations. So this dislocation, sorry, stacking fault energy determines the distance between these partials. Okay, now please repeat. So I said that the dislocation partial creates some region which is called as the stacking fault, and the created region stacking fault possess some energy. So that energy depends on the Berger vector and the distance between these partials. So that energy is inversely proportional to the distance between these partials. 1 by d. So if in the question we have asked that what determines the distance of separation of these partial. So distance of separation is inversely proportional to the stacking fault energy. So we can say that stacking fault energy determines the separation of these partials. Is it clear now? Is this stacking fault energy the same energy that was reduced during the dislocation? Uh, yeah, so stacking fault energy is the same, but it is less than the energy of the dislocation, energy of the previous dislocation. So it is less as compared to the previous the full dislocation, but the region between these partials contains some energy, so that's why we call it as stacking fault energy. Okay, so we'll move to next question. So in this question, we have asked that show that the reaction is either vectorially correct or incorrect. So vectorially correct we see by the addition of these terms. So if we take as so if we add these two terms, e by 6 to 1 bar 1 plus a by 6 1 1 by 2. So the 2a by 6 and 1a by 6 will give 3a by 6, and 1a by 6 1a by 6 will be 2a by 6, and this will be minus a by 6, and minus 2a by 6 will be uh, minus 3a by 6. So we can uh, take common. 3 by 6 will be 1 by 2. So this will be a by 2, 1. Here it will be 3. So a by 6, a by 6, 2a by 6, that will give 2, no, 3. And here it will be bar 1. So here we can see that the middle indices of both vectors is adding, but here we have zero component. So either it should be minus 1, but given by this Miller indices, we can see that it is not vectorially correct. So if we want to find that is the reaction energetically favorable or not, so we'll calculate the energy. A square by 4 minus square plus 0 plus 5 square. So this will be 2a square by 4, a square by 2, and here it will be a square by 36 into 6 plus a square by 36 into 6. So that will give a square a square by 3. So if we check it is energetically favorable or not. So because of the square term, we are getting less energy after the reaction. But here we should have minus 1. So either it is 1 minus 1 and minus 2, then only it will be 0. So then both the vector, it will be both vectorially correct and energetically favorable. Okay, so we will move to the next question. So in this question, we have asked that Burgess vector of a crystal generally lies in a close packed direction. Why? So uh, we have studied in the previous lecture also that the Berger vector should be the smallest lattice translation. And the smallest lattice translation will only happen in the close peg direction. That's why we have Berger vector of a crystal on the close peg direction. So the close peg direction have the smallest lattice translation. Like if we check it by taking example of BCC and FCC. So for FCC, the close back direction is 110. 110 is on the, so 110 direction is if this is Z, X, and Y. So the 110 direction lying on the bottom of this. So this is 110 direction. So if we take, so this is, we are getting, means all atoms are closely packed in this direction 111. Or it can have multiple, means this is the, so the family of direction is written as the angle bracket 110. And if we want to write a single direction, we can write it as square bracket for a single direction. If it is on this plane, so this will be y and z, so 0, 1, 1. And if we have on this plane, so it will be 1, 0, 1. Or either it can be minus and plus also. So we will check it later, but for now, we are just considering whether the 110 direction is closely packed or not. So the 110 atom is 110 direction, three atoms are coming. So uh, it will have smallest lattice translation from one atom to another atom. And in the dislocation motion, we see the bond breaking from the previous atom, and the half of the plane, extra half plane, will make new bonds from the further layer. So this much amount, the extra half plane, it should travel from here to here. So that is the smallest lattice translation. That's why the Berger vector for this also is the distance between these two atoms. So it is occurring on the close packed directions. Similarly for BCC also, we have atoms at corners and one atom at the uh, body center. So when we draw a line from body diagonal, so we can see, means here this is A. So and the body diagonal is root 3 A. So here on the body diagonal, we have three atoms like this. So the distance we have to travel is root 3a by 2. So it will be around 1.732 a by 2. So it will come less than the a. So it is less than the a. So that's why it is the smallest lattice translation in body diagonal. So we define the Berger vector for BCC along the body diagonal. Next question we have asked that what is the ideal strength of a crystalline solid? Uh, so the ideal strength of a crystalline solid in the uh, I so crystalline solid, so ideal strength will be strength at which no defects are present in the solid. So the that ideal strength is generally given as the pulse Navarro stress. So the pulse Navarro stress is given as for the deformation 2g divided 1 minus nu exponential of no, this is we not pulse Navier stress. The pulse Navier stress comes when the dislocations are present. So the theoretical strength is given by G by 2 pi. So G is the shear modulus of the material. So this depends on the only shear modulus of the material. So that's why it is highest for all materials when no dislocation is present. And next statement is that what crystal imperfection allows the material to deform at much lower strength and why? So the dislocations are the crystal imperfection which allow the material to deform at much lower strength and why? So why? Because we know that the Berger vector is the smallest lattice translation. So by motion of the using the Berger vector magnitude with smallest lattice translation, we can uh, continue the deformation of the material. So by step-by-step motion of the dislocation, we can easily deform the material. That's why the uh, dislocation decreases the ideal strength of a crystalline solid. Okay, so next question we have asked that on what planes of a BCC structure can the A by 2 111 move? Yeah, so first we draw the BCC structure. So the atom at body diagonal, if we want to draw a imaginary plane, so this plane have the maximum atomic density. So yeah, so for a slip dislocation slip and glide, we need uh, first is the highest atomic density plane and the direction. So both plane and direction should be the highest atomic density. So if we consider the uh, so direct plane will give highest atomic density. So the planar sorry planar density of this plane. So this plane is generally the 110 plane. So the plane will be let's start. So this plane, number of atoms on this plane is the two means four atoms are sharing only one fourth. So one fourth into four will be one, and complete atom at the center will give two. And the area of this is the this is A, this is root 2 A. So root 2 A and A will give root 2 A square. So the planar density will be number of atoms per area. So this will be 2 root 2A square. And for confirmation, if we want to calculate the uh, planar density at this 100 plane, so the planar density will be at number of atoms is 1 and the area for that will be 1 by A square. So this is giving root 2 by A square. This is only 1 by A square. So this is so the planar density for 110 is greater than planar density for 100. So this is the close packed plane. And the linear density, if we want to calculate, so along the body diagonal, we have so we for the linear density we calculate from the center of the atom. So from the center of atom, we have number of atoms 2 and the distance is uh, A, sorry, R, 2R and half of R. So 4 radius or capital R we can say. And the capital R of the BCC generally equals to, so this is 4R equals to root 3A. So we can say root 3 by 4A. So the linear density for, so number of atom by the distance, this will be 2 by 4R. And if we want to consider for this one is any 100 direction, so the number of atoms is 2. No, number of atoms is only 1. So for the 100 direction, so this is along a 110 direction. No, so for the BCC, the direction will be this. From the this is center, so direction will be the this body diagonal. So the direction is body diagonal direction is 110. Sorry, 111. So this is for 111 direction, and for 110 direction, we have number of atoms 1, and distance is 2r. So here also we are getting r is the root 3a by 4. So this will be 2 by root 3a, and for this we write for this also 1 by 2r. So the distance also for this is same. Uh, yeah, sorry for, so we can see just the number of atoms lying on the uh, that direction. So the number of atoms on 111 is greater than on 111 direction is greater than number of atoms along 110 direction is less. So the linear density for that is higher along BCC. So the on what planes? So the plane for the A by 2 111. Yeah, so A by 2 is the half of this distance. Means this is 111. So half of means Berger vector it have should travel from this atom to this atom. So along the 111 direction, the lattice shortest lattice translation is A by 2 111. So this so for so the plane for BCC structure will be 110. And for BCC, there are two other planes also, like 112 and 123. So, but these two planes generally activated at higher temperature. So, at room temperature, we have 110 plane for the A by 2 111 direction. Okay. So, we will move to the assignment questions. So, do you have any doubt, or we can proceed to the questions? Okay. So the first question we have asked, that climb of edge dislocation is influenced by. So can you guess the answer? Option 1 and 4. Yeah. Vacancy migration and temperature. So diffusion of atoms also happen in the vacancy migration. Means atom move to the vacancy and vacancy move to the atom place. So second option is also correct. So first one, two, and fourth option is correct. Second question we have cross-slip of a screw dislocation occurs when either this dislocation move from one slip plane to another, resolved shear stress is sufficient in the new slip plane, and the vacancy diffusion assist movement or Berger vector remains constant. Okay. Yeah, so cross slip we studied in the last week also. Like a cross slip occurs in the screw dislocation, so it move from the its principal slip plane to another slip plane. And so to for motion of the screw dislocation on the secondary plane requires the sufficient shear stress amount uh, for the motion. So the resolved shear stress should be sufficient in the new slip plane. So second option is also correct. Third option saying that vacancy diffusion assists the movement. So vacancy diffusion happens in the climb process, not in the cross slip. So the third option is correct, incorrect. And the Berger vector remains constant in every situation. If it is cross slip climb in the screw or the edge dislocation, so Berger vector will not change. So we can say that the first and second option is correct. First and second option is correct, and fourth option is also correct. Berger vector remains constant. Third question we have asked that two indices of 2111 plane in an FCC crystal that contain the screw dislocation with the Burgess vector A by 2 10 bar 1 is used. Uh, so for finding the dislocation planes, glide plane to for that Berger vector, we do dot product with the Berger vector and the plane. So Berger vector will should sorry the dot product for that will be 0. So which for which option the dot product is 0? Option 4, yes. 111 and 1 minus 1 will give the 0 dot product. Or we can check in the Thomson tetrahedron also. So, but just for the easy process, we can do the dot product. Fourth option is correct. Question 4 say that the figure below illustrates a transformation from state A to B. Which of the following statement accurately describe this transformation? So first we have the extra half plane in state A with three atoms, and in the B position the atom got reduced to two. So the vacancy here comes at the atom position and atom goes to the vacancy position. So what which climb process it indicate? Option one, as the dislocation climb up by vacancy diffusion. And one more thing is that the when vacancy is coming to the dislocation plane, so it is called as the vacancy sink. Means as dislocation is acting as a vacancy sink. Means the vacancy is coming to the as dislocation, and when the vacancy goes from the edge dislocation to the another lattice site. So that is called as the vacancy source. Means the edge dislocation is creating vacancy in some other plane after the climb process. So in that situation, we will call it as vacancy source. But here vacancy is coming to the edge dislocation, so we can see it is act as a vacancy sink. So first and the third option is correct. Fifth question we have asked that the motion of screw dislocations in a BCC crystal is often termed as a pencil glide because of, yeah, so pencil glide means the motion of screw dislocation is uh, random. Yeah, so we can say that we just now discussed that BCC crystal have three planes and one direction. Here, yeah, here we have one moon Berger vector direction and three planes. So when the screw dislocation on this A by 2110 Berger vector moves on these planes randomly, so that creates as a pencil glide. Pencil glide means movement is like this, the screw dislocation. So that's why it is called pencil glide. So so the option for this, the glide along A by 2111 in 110, 112, and 123 planes give the pencil glide. So second option is correct for this. Okay. So coming to next question. The formation of the jog. So jog and kink forms when the two dislocation interact. So in the jog means if the two dislocation, so this is one dislocation one, this is a line vector, this is Berger vector B1, and the second dislocation is like this. So the line vector for this is along T2 and Berger vector, sorry. So for this, the line vector is along this and Berger vector in this direction. So when these two dislocation interact, because this is coming in this direction and this is going in this direction, so that create, so this dislocation one will create a jog in the second dislocation after interaction between these two dislocation. So they means this is a second dislocation. So the dislocation will one will displace the dislocation two in this z direction. So it will be means one step is created along the dislocation two line. So the line vector will be T2 and Berger vector for this is B2. So as the line vector Berger vector is still perpendicular to each other, so it this create a jog, and the characteristic of jog is also that so this is the single plane when it displays it, so this is creating a step after the plane, so the uh, displacement after the plane is called as the jog. After interaction, if it is out of plane, so it is called as jog. And for the that first dislocation, first dislocation because the Berger vector for 2 is in this direction, so the it will displace like this. So this is T1, this is T1, and this is T1. And Berger vector for this is down. So this is also a jog created for the dislocation 1. So the out when displacement is out of plane, it is called jog, and when displacement is in plane, will be is called as the kink. So the jog and kink we will further discuss more in the next class. So for now, this is sufficient to know. Like so for so the in this creation of jog and kink is extending the dislocation line, means the dislocation line length is increasing. So as the dislocation line length is increasing, uh, it increases the energy of the dislocation, and the it also creating a step in plane or out plane. So that step helps in the climb process. Means climb is general means this is the dislocation line. If one obstacle is here, so this is the climb, and it surpasses the obstacle in the path of this motion. So this climb is a case of double jog. So this formation of jog also helps in the climb process. So from the options given here, We can say the formation of jog increases the energy of the dislocation and adds the climb process. Okay, you can see screen. I will reshare it. Can you see my screen now? Okay, then I will continue. So the this formation of jog increases the energy of dislocation and adds the climb process. Going to the next question. So here we have to match the column. So Berger vector is what? So it is along closest packed direction. So for one, second option is matching. S dislocation, climb. Screw dislocation can cross slip. Kink have both edge and screw character. Yeah, so for this process, It is displacement in plane, so it is kink of edge character. So 1 to second, second to third, third to fourth, and fourth to 1. So the fourth option is correct. Next question. We have asked the planar density of atom for 110 plane in FCC, in iron FCC and iron BCC crystal with edge length A is. So for FCC, the 110 plane gives number of atoms are 2, and this is root 2a, this is a. So area is the root 2a square. So the planar density will be 2 by root 2a square, giving root 2 by a square. For BCC 100, yeah, sorry, I have. So this is for BCC, and this is FCC 110. So for FCC 110, we have atoms like this. One atom and one atom. So half of the, so the atoms at the corner giving one complete atom, and atom from on the face center is giving half and half one. So it is two. So Athav, can you see my screen now? Okay. So we were at question number 6. So the formation of jog. So yeah, if the interaction gives the placement out of plane, it is jog, and in plane it gives kink. So the dislocation one is getting displacement in the same plane as previous plane. But the character of this is line vector and this is the Berger vector. So the this will be kink, and because the line vector and Berger vector is perpendicular, so it is giving edge character kink. But for this, this is giving the jog. So jog will always be of edge character, but kink can be to both types, edge or screw character. So the formation of the jog gen, helps in the climb process to occur. So for this option, and because of the line length of the dislocation is increasing, so that increases the dislocation energy also. So the first and third option is correct. Increases the energy of dislocation and adds the climb process. Okay, okay, no problem. So can we move to the next question? The sixth question is clear. Okay. So seventh question, we have to match the column. So for Berger vector, we know that it is along the closest packed direction. So edge dislocation, it uses climb to change the plane. Screw dislocation cross slips, and kink have both edge and screw character. So if we match this by so first to second, second to third, third to fourth, and fourth to one. So the D option is correct for this. Okay, so next question we have asked the planar density of atom for 110 plane in iron FCC and iron BCC crystal with edge length A. So for BCC crystal, the 110 plane is shown like this, means four corner atoms and one body centered atom. So for this, number of atoms is 2 and area is root 2 A square. So this gives the planar density, number of atoms per area will be root 2 pi A square. And for FCC, the 110 plane is shown like this, means four corner atom and two face centered atom. So four corner atom will give 1 and the two half of face centered atom will give 1. So there are two atoms and the area will be same, means root 2 A square. So the planar density will be 2 by root 2 A square. Oh, this give root 2 by A square. So the atomic arrangement for the BCC and FCC is changing, but the planar density for both BCC and FCC along 110 plane is same. Only atomic arrangement is different. So the second option is correct for this. So in the planar density, just we have to calculate the number of atoms and the area of that plane. So coming to next question, which of the following represents possible slip systems for any BCC crystal? So BCC crystal, we know that the Berger vector have A by 2, 1, 1, 1 direction. So we can say that we have two by 1, 1, 1 direction, and we have to check the dot product, zero dot product for the respective planes also. So if we do a dot product, so this is giving 0, and for this also it is giving 0. So the B and C option is correct for this. So next question is that here we have asked that the figures show the variation of displacement delta U across a dislocation in a slip plane as a function of x. It can be concluded that uh, the figures show the displacement of the dislocation on a slip plane. So displacement is getting 0 with the distance from the dislocation core. Means the displacement is only limited to the nearest place of dislocation core. But in the second, yeah, we can see displacement is limited or constrained, we can also say. But for the B option, the displacement we can see up to extended distance from the dislocation core. So displacement is dispersed. So any dislocation which have dispersed displacement in the atomic planes, so that have the so that is called as the wide dislocation. And the dislocation which have constant displacement is called as the narrow dislocation. Yeah. So the narrow and wide, so the movement, if we compare the dislocation motion of these two narrow or wide dislocation, so wider dislocations generally require less stress for the motion. So they are easy to move. So this is generally we found in metals. And narrow dislocations are hard to move. So the narrow dislocations are generally found in ceramics. So from this concept, we can say that the dislocation movement is easier in B than A. So second option is correct. And one more thing that the wider dislocation have a larger interplanar spacing, easy to move wider dislocation and large interplanar. Interplanar means the distance between two planes. And here, small interplanar spacing. So the B dislocation will have larger planar distance as compared to A. So C option is also correct. Yes, so I said that uh, we can see in the picture of A that displacement is getting zero when we move from the dislocation core, when we move away from the dislocation core, so it is getting zero. So the displacement is constant near the dislocation core. But for the B picture, we can see the displacement is continuing as we move away from the dislocation core. So displacement is dispersed. So this dislocation is generally known as the wider dislocation. And for the A option, sorry, for the A picture, the displacement is constant. So it is called as the narrow dislocation. So the narrow dislocations are require very high stresses to move. So they are hard to move, so this is generally found in ceramics, and the so means elements which have small interplanar spacing also have narrow dislocations. But for wider dislocation, they are easy to move, and they have larger interplanar spacing. So the larger interplanar spacing in wider dislocation is generally found in metals. So from this concept, we can say that the dislocation movement is easier in B than A, and the B have larger interplanar spacing as compared to A. So is it clear now? If your Wi-Fi is lagging, you can see the recording also later. Yeah, so this is the 10th question. Next, next question is how many different 111 planes are there in an FCC system? So for FCC system, 111 planes are of four types. Sorry. So the four different 111 planes are found in FCC system. Next question is the cross slip of a screw dislocation occurs. So the cross slip of dislocation requires dislocation motion from one slip plane to another. Second option saying that normal stress acting perpendicular. So this is wrong. Vacancy diffusion assist movement. This is wrong. The Berger vector varies. This is also wrong. So only first option is correct. Dislocation moves from one slip plane to another. Uh, Next question. Which of the following statements correctly describe the effect of jog formation in a dislocation? So this is same as previous question. So it increases the energy of dislocation. It facilitates the climb process. Next question we have the factors that don't affect Pulse-Navarro stress. So if we write the Pulse-Navarro stress formula, this is 2g by 1 minus nu and exponential of minus 2 pi w by b. So in this equation we can see that all are, so here w is the a by 1 minus nu. So a is the interplanar spacing. So all parameters are dependent on the material properties. So from the options, first option is saying periodicity of atoms. So it requires periodicity of atoms required for the pulse number of stress. Dislocation width is also, this is W is the width only. Crystal structure also affect this stress, and only the applied stress does not affect the personal stress. It is constant for a material. So the fourth option is correct. So Athar, you can see my recording. So I will end the session now.